Okay, in past videos, we talked about why standing waves occur when multiple reflections go back and forth on each other, and why only certain geometries will lead to standing waves. What I'm going to work through in this video is the mathematical relationship between the length of a string that is fixed on either end and the standing waves that can occur on that string. Now, what we discovered when considering the geometry and looking at how these waves bounce back and forth at each other is that if a string is fixed on either end, that means that it has two fixed end reflections. And what we know that means is that we must have a node at either end of the string. So what we're going to do is we're going to work through the simplest patterns that can make that happen to more and more complex patterns, and then hopefully we'll see a relationship that is clear. What I'm going to say here is that the length of this string we'll call L. Now, to help us with this, I'm just going to draw over here on the side a sine wave. So if I have to go from a node to the next node, the simplest pattern that I can imagine existing on the string is going straight up and straight down like that. This is an arbitrary choice. I could have just as easily drawn it below the axis like that. Either way, the relationship remains the same here. In this case, L is going to be equal to, if this is a full wavelength, this, which works out to be half of a wavelength. So the simplest, often referred to as the n equals 1, the fundamental frequency, or the first harmonic, is half of a wavelength is equal to the length of the string. There are a lot more patterns, though, that get us two nodes. So let's go to the second simplest. This time we're going to go up, down, and come back up, and we're going to end at not the first node we run into, but the second one. So this is going from a node to another node, but this time it's going to have one node in the middle as well. These, by the way, are the antinodal points that will exhibit extreme variation. And again, this is an arbitrary choice. I could have drawn it going down and then up. And if we imagine, that shows us what our wave is going to look like over time as this top spot varies to the bottom and back up and back. This is called the n equals 2, the second harmonic, or the first overtone. Second harmonic would be the physics name for it. First overtone would be the music name for it. By the way, this was the first harmonic, or the fundamental frequency. Okay, anyways, with those definitions, back to this. The length of this string, we can see this time, represents one full wavelength. So this is going to be the length is equal to the wavelength. Now we know the answer here, so I'm going to put this in a different form to help us see the pattern a little bit more easily. Specifically, instead of referring to that as one wavelength, I'm going to say that it is 2 halves of a wavelength. Now we know 2 over 2 and 1 are equivalent, so that's okay. But what we can do now is we can see a little bit of the pattern. This is L equals 1 lambda over 2, 2 lambda over 2. So if you're paying attention, you might guess that the next one is going to be 3 lambda over 2. But let's just do it and show how that works. So here's our string fixed on either end. And this time, we're not going to stop at the first node. We're not going to stop at the second node. We're going to go all the way to the third node. And so we're going to use this shape right here. Okay, we end up with a node, 2 more nodes, and this time 1, 2, 3 antinodes. Anyways, this is the n equals 3, the third harmonic. and the second overtone. For most instruments or things like that, this by far would produce the most power. These would produce less power. As you go up into higher N, you would hear less and less of that note if you played the string, but they're there. The length in this case is equal to one full wavelength plus an extra half, so we would say it's equal to 3 lambda over 2. Hopefully at this point we can see the pattern, specifically that for any harmonic, L is going to be equal to n lambda over 2, where n is an integer, 1, 2, 3, and so on. Any of these relationships will work, and what that means then is if you pluck a guitar string, this is the way it will vibrate the most, but it will also vibrate a little bit like this and a little bit like this. If you were to take a special device like a oscilloscope or something like that physicists use to look at frequencies, you'd see most of the sound being produced is corresponding to the wavelength and frequency that would correspond with that. This is the second, and this is the third most common. Anything that doesn't meet this geometry, as discussed in previous videos, the incident wave and reflective waves would add up in ways that were random, and that randomness would cancel out over time.